Okay, this is going to be a video that uses probability statements to determine whether or not two events are independent. We're going to look at two situations we've looked at earlier in the week, and we are going to determine if the two events in the two-way tables are indeed independent or are they not independent. First, please turn to page 27. Read the information and use that information to fill in the two-way table. Please pause the video while you do this. Okay, so I'm creating a hypothetical two-way table. So the first thing I'm going to do is it's a 1,000 table. So I'm going to put in 1,000. Oops, what the heck, man? I'm going to put in 1,000. In the bottom right corner, and I see that 75% have seen the ad, so 75 and 1,000, and then 40% are going to New York, so this is going to be 400, and using subtraction, I can get 600 and 250, and I also know that 15% did not see the ad and are not going to New York, so this is going to be 150, and by subtraction, 450, 300, and 100. Okay, let's look at number 2. Based on the two-way table, describe two conditional probabilities you could use to decide if members who saw the online ad are more likely to plan a vacation in New York compared to those who did not see the ad. So the ones I'm going to look at are you going to vacation in New York if I know you watched the ad? And I actually don't like this one. I think I'm going to change it. And I'm also going to look at, are you going to vacation in New York if you did not watch the ad? And then what is the overall probability that you are vacationing in New York? That is really annoying that it keeps jumping it up. All right, so I see that the total number of people who say they are going to, that they've watched the ad is 450. Sorry, 750. And of those 750, 300 of them have watched the ad. And when I divide that, I get 40%. Now, I see that the people who did not watch the ad, that's 250. And of those 250, 100 of them plan to vacation in New York. So let's throw that into the calculator. 100 divided by 250, I think is also, yep, 40%. And the overall probability of vacation in New York, I'm told, is 40%. So what I'm seeing here, number 4, do I think the ad campaign is effective? No, I do not think the ad campaign is effective. I cannot spell, even with it right there, is effective because the people who watched the ad had the same probability as those who did not. Okay. And this is really going to lead into what we are doing today with using probability statements to determine if two events are independent. So what we're going to do first is we are going to just look at some scenarios and identify the two events and just kind of think to yourself, could there be a connection? So on page 28, 1A states, are high school students whose parents set a midnight curfew. So in other words, is setting a midnight curfew, if you have a midnight curfew, does that affect the probability you are going to have a traffic violation? Is there a connection? Again, this is opinion, so you can jot down whatever you like, yes, no, whatever. B, are left-handed people more likely than right-handed people to be interested in the arts? So we could create a two-way table where one side says left-handed, right-handed, one row says left-handed, one row says right-handed, and then we have a column that says interested in the arts and a column that says not interested in the arts. Are students who listen to classical music, so again, do you listen to classical music on one side? Yes, no. Are you interested in mathematics? Yes, no. And we could fill in data for that. Are people who play video games more than 10 hours a week likely to say that football is their favorite sport? And again, we could have one side of our two-way table where we write down how often, how many hours per week people play video games versus what their favorite sport is, or is your favorite sport football? Yes, no. So today, what we are going to do is we are going to look at some familiar scenarios, and we are going to determine if the events on the two-way table are independent events. And the way we've determined if events are independent is we are going to look at the probability of an event occurring, and then the probability of an event occurring if we have a given condition. So here's how it's going to work. We know that two events are independent if the probability of event A equals the probability of event A given that something else has occurred. So in other words, knowing event B has occurred doesn't change the probability of event A occurring. Okay, a good thing to think about with independent events are something like if you flip a coin and you roll a die. Flipping heads or tails is not affected by how you spin a spinner or how you roll a die or a spinner. Those are independent events. One does not affect another. Rolling a 2 on the die is not going to change the probability of getting heads or tails. They are completely independent events. Knowing what you roll does not affect how you flip the coin. Now, the complement of that is not independent events. And I want you to notice that I'm not using the phrase dependent events. That's a whole nother test that we are not going to get into in this class. If we have not independent events, we're not proving them dependent, we're just saying they're not independent. What that is going to be is if the probability of event A is not equal, and I don't have a not equal button, so I'm just going to type not equal to event, the probability of event A given that B has occurred. Okay, so in other words, knowing that event B occurs changes the probability of event A occurring. Okay, and a good example of dependent events, just with an easy game situation, is if you have a deck of cards, as soon as you deal out a card, if I know the other person has 2 aces, the probability of me getting an ace goes down because I know that those aces are no longer in the deck. Okay, cards in general are not independent events. See, I almost got tricked. Because knowing what the other person got is going to change the probability of the other event. So let's examine some familiar situations. So we looked at this scenario the other day, the students at Rufus King High School, and do they participate in after-school athletics or not? And are they male or female? And now what we're going to do, if you look down here, they actually do define, where is it? Let's just be standard here. Oh, here we go. Now we're going to use F for female and S for male. I see it on page 30, so we might as well just use it here. We're going to use This is going to be female. So this is going to be not female. This is going to be they participate S. And this is they do not participate S prime. And I just saw those on page 30. I'm just going to use those standard notations because that's what we're now using instead of A and B. So it says, for each of the following, indicate whether the probability is one that can be calculated using the values in the table. Also indicate whether or not is conditional. So letter A says, what is the probability that a randomly selected student so that's just the probability of S, and I can calculate that. It's not conditional. B, the probability that a randomly selected student who is female condition participates. So now I'm looking for the probability that they participate given that they are female. The probability that a student who is male condition participates. Oh, and I can do this with the table. So they participate given that their male is going to be the complement of female, and I can also calculate this. Number 3 says use the table to calculate each of the probabilities. So this is looking a little familiar. The probability of participating in after-school athletics from the table, that's 400 out of 1,000, and that's going to be 40%. The probability, so here we go, who is female participates. So let's see here. If I look at my table, of all the females, there are 580 females, and 232 of them participate. When I divide that on my calculator, I get exactly 40%. The probability that a student who is male participates, so participates given not female, there are 420 males and 168 of them participate. When I divide that with my calculator, I also shockingly, but not really, get 40%. I'm feeling a pattern here. So number 4 states, would your prediction of whether or not a student participates in the after-school athletic program change if you knew the gender of the student? No. Probability of S given F equals the probability of S given not F, which is 40%. It's always 40%. Doesn't matter if I know the gender. So now we're going to actually formally state this obvious statement. We are going to state that gender and participating in after-school athletics at this school is independent. So we got to be careful. It says based on the definition of independence, and let's remember that that is the probability of A has to be the same as the probability of A given a condition. They have to be equal. So I'm going to say the probability of participating equals the probability of participating given that you are female. Therefore, the events are independent. The events, gender, and participating in, I can't type this all in, after-school athletics, we're just going with participating, are independent. Okay, so in other words, knowing someone's gender does not affect whether or not they participate in after-school athletics. Right, so a randomly selected student is female. What is the sorry, let me rephrase that. A randomly selected student participates in the after-school athletic program. What is the probability the student is female? So if I know you're participating in the after-school athletics program, so, oops, pen please. Probability of female given that I know you participate. So participates, there are 400 of them who participate. and 232 are female. And when I divide that out, I get 58%. Using only your answer from part A, what is the probability that this student is male? So here, I know that the complement of participating given, female given participating is the complement of not female given participating. So I can just say 100 minus 58, which is 42%. All right, let's look at another situation we looked at recently. Let's look at the situation of, do you have asthma and do you live with someone who smokes? Let's just quick see if we are defined. They want us to define these two events any specific way. No, they do not. So I'm just going to go with A for asthma, A prime for non-asthma. S for you live with the smoker. S prime, you do not live with the smoker. We are asked to calculate, are the events a randomly selected student has asthma and a randomly selected student has a household member who smokes, are these independent and what probabilities could we use? So really the question is, if I know you have asthma, if I know the probability of having asthma, is that the same? Oops. What that little thing is. Is that the same as having asthma if I know you live with a smoker? So let's take a look. The probability of having asthma is 182 out of 937. And when I divide that, I get 19%. Now the probability of having asthma, if you live with a smoker, so in other words, I'm only looking at this column. If you are one of these 395 people, there are 113 of them. Toss that into your calculator, and we get 28%. So with good mathematical vocabulary, I want you to pause the video and write up a conclusion for number 9. Right. At this point, you should have tried this on your own, so let's see how good your sentence is. So I'm going to say the events having ASTHMA and living with a smoker are not independent because P of A does not equal, actually, no, I'm just going to put the numbers in. It's easier. Equals 19% and P of A given you live with a smoker is 28%. They are not equal. Living with a smoker changes, affects, does something, I don't know, but it's not the same. Ran out of space. All right. Fantastical. Why does it do that? All right. Is the probability that a randomly selected student who has asthma, given condition, who has asthma, has a household member who smokes, so let's see, the probability smokes given asthma, is this the same as the probability that a randomly selected student who does not have asthma, so the probability not having asthma, have a household member who smokes? I don't know. Let's find out. So if you have asthma, there are 182 kids with asthma. And of those, 113 of them live with a smoker. When I divide that out, that is 62%. If I know you have asthma, you have 62% chance of living with a smoker. Now, if you don't have asthma, there are 755 of those students. Of those 755, and again, I'm going to just scroll up here. For the first one, I was looking here at this row. All right, and I'm saying of these people who have asthma, here are the people who live with a smoker. Now I'm looking at the people who don't have asthma. And I'm going to pull the probability that they do live with a smoker. So I'm still in the do you live with a smoker, but I'm on different rows. So 755, and we said it was 282. And that is 37% on my calculator. So is the probability the same? No. No, it is not. No. Students with asthma are more likely. Now, again, it's okay to say they're more likely. We're not saying living with a, one causes the other. We're just saying that statistically, using probability, it's more likely. We're not saying one causes another. We're not getting into causation here. You're just more likely to live with a smoker. So just be careful with your vocabulary. We're not using causes. We're saying it's just more likely. A student is selected at random. The selected student indicates that he or she has a household member who smokes. What is the probability the student has asthma? We've actually just done this. We did it already. If we know you live with a smoker, like we just did it up above, if we know you live with a smoker, the probability of having asthma is 28%. Okay, obviously, go back, rewind, rewatch any part of this video you need clarification on. You have homework tonight in your packet. Go ahead and get started on that. And the answers will be posted online. Homework is page 26 and also 32 and 33.